Okay, welcome back Physics 30s to our next lesson in Chapter 6. This is 6.5, and today we're going to be looking at hydrogen's energy levels. Okay, so let's put the nucleus of hydrogen down here, and now we're going to draw all the energy levels above it. This represents all the places that the hydrogen electron can be. I'm going to put these numbers with n on the left side here, and n equals 1 is the ground state, and as we go up, that goes into the excited states. So the hydrogen atom normally lives here in that first shell. Now I'm also going to put the energies on the other side. This shows the energy amounts of each of those shells. And we'll talk a lot about these shells or levels, but the first thing I want to talk about is the energy. As I mentioned before, the electron is most stable in its ground state of n is equal to 1. All the ones above it are considered to be excited states. Now let's take a look at the energy numbers first. First, you notice that at the top it has 0 electron volts, and as we go down, it gets more negative. The reason we're using negative is that up here, by the 0 electron volts, this is considering when the electron is unbound to the atom. It's knocked off, it's completely free. At that position, it would have no potential energy because it's considered not attached to the hydrogen nucleus. So if we have no potential energy here, and it's falling towards the nucleus as we go further down, just like an object falling with mass on Earth, you lose potential energy as you go down. So if we're starting here at negative, we're going to have our energy levels as negative as we go further and further down. So the difference between being free from the nucleus and being in its ground state is 13.6 electron volts. Now let's look over to the left side where I have the n values. Starts with n is equal to 1, then 2, 3, 4, that seems to make sense, but then I wrote n is equal to infinity. So what this means is that there is actually a whole bunch of other energy levels in here. Now you probably noticed that between 1 and 2 is the biggest gap. Then 2 to 3 is smaller, 3 to 4 is smaller, and we will get continually smaller gaps as we move up. So there would be an n is equal to 5, 6, 7. As we can see, these are getting super close together. And in theory, there's an infinite amount of levels until I get to the electron volt level of 0, or when the electron is free of the nucleus. Now let's look at when there's changes to the electron, and we have jumping up and jumping down between states. First, the electron begins at the ground state, as we've said before, and it's going to jump up to an excited state when it receives energy from an electron or a photon. Remember, receiving energy from the electron was when we were shooting it with a current and we were getting emission spectra, and when it was absorbing energy from a photon was in absorption spectra. Let's show this with the energy of a photon. A photon comes in with enough energy and it knocks the electron up into an excited state. We saw that this went from n is equal to 1 to n is equal to 3. You could get a question that says how much energy is required to go from n1 to n3. This is actually a pretty simple question. All you take is the energy level here, 13.6, and the energy level here, 1.5, subtract them, and you would get 12.1 electron volts. So that must have been the energy of the incoming photon. Now remember that if it didn't have this much energy, maybe it only had 11.5 electron volts. It can't knock the electron in between two shells, so this photon would just continue to pass through and it would not transfer its energy to the electron. Now, given these values, you might be considering, what if we hit it with more than 13.6? Say we hit it with 20 electron volts. What would happen in that case is, well, this would have to be a shorter wavelength of photon. It would come in with lots of energy like this, and it would knock the electron clean off of the hydrogen nucleus. The animation wasn't quite right. It doesn't spend time in between, but it would be knocked completely off of this nucleus, which is called being ionized. So the electron is ionized and leaves the atom with any energy greater than 13.6 electron volts. We saw this when we were talking about the work function in the photoelectric effect. What's nice is there, we also used the work function as a negative value, that you had to overcome this negative 13.6 electron volts to liberate the electron or knock it off the nucleus. Next, we'll look at when it jumps back down. When the electron jumps back down, it emits energy as a photon in the energy level difference. So if it jumps from N2 to N1, it would give off the difference between 3.4 and 13.6 volts. So it would give off 10.2 electron volts in a photon. Now I put that there as bright purple because anytime it's going to drop down to n is equal to 1, that's so much energy that we're going to be into the ultraviolet range. This one is the biggest jump. We can see this longest arrow, so that would be the most energy photon, but all of these are going to be in the UV range, so we can't see those. So I just put off to the side here, hydrogen dropping down to n equals 1, all of those are going to be UV. Still different wavelengths, but all of them are in the UV range. When it drops to n equals 2, we're going to start seeing some visible light and we would get a bright line spectra. So if it drops from 3 to 2, we would get red, drops from 4 to 2, we would get green, and various colors like this. Now a question could ask you, what is the frequency emitted when we drop from n equals 3 to n is equal to 2? So how we would calculate this is we would start with the energy change. The difference from negative 1.5 to negative 3.4 is 1.9 electron volts. So that will be the energy of the photon. Next, we'll use our formula for energy of a photon, E is equal to hf, and plug in our values. Now, energy I'm putting in as 1.9 electron volts. So when I put in my H, I put in 4.14 times 10 to the negative 15. This is the Planck's constant version for electron volts. You could convert to joules as well, but I think since we already have electron volts, this is the easier number. I divide that over on the left, and I get a number of 4.589 times 10 to the 14 hertz. If this asks for wavelength, we can just convert that with the universal wave equation, and I would get 654 nanometers, which is red light. Now, just before we leave this slide, you might be wondering, what if it drops to n is equal to 3 or n equals to 4 or n is equal to 5? If it's dropping to n equals 3 or anything less than that, this is going to be too small a frequency to see. So getting into the infrared and further past that. Okay, so let's look at another type of question that you could be asked. In this diagram, we see a lot of different drops of an electron through different shells. And it could say, which creates the smallest wavelength? I'll give you a minute to think about that and see what your answer is. The answer is going to be this drop right here. And how we would reason through that is that, well, the smallest wavelength would have the most energy, which would be the biggest jump from shells. The biggest difference in energy levels on this side gives the biggest energy photon with the smallest wavelength. Now, lastly, I just want to look at absorption versus emission in this diagram. So electrons can absorb energy from the ground state to any other state. So this would look like this. It can go up from the ground state to, let's just start with looking at N1, 2, 3, and 4. We won't look at all these tiny ones above. So it could absorb wavelengths of these three energies. So that would be the wavelengths it can absorb. For emission, electrons can jump down between any energy levels. So it could jump down the same levels that it absorbed there, but it could also go in between. So these blue arrows are showing all the wavelengths that it can emit, and hopefully we can see that there is more than it can absorb. So I put on the side here, atoms can emit more wavelengths than they can absorb. And that's all the information I wanted to go through for today. Just one last important note, that the energy shells are all different for different atoms. So these numbers will not be the same for every different atom. This is just specific to hydrogen. We're using it as an example because it's a fairly simple one. But that's it for today's video. I hope that helped you to understand jumps between different shells. Thank you so much for watching this video, and I will see you in the next lesson.